so that we don't miss a thing. So, welcome back. Hello, Emmy. Good to see you. Not everybody has finished homework, so we're not able to go over that as a group. But if you have any questions about why you missed something, or if you think that there's a problem in the answer key, please let me know and I'll be happy to talk about that with you. Let's do the standard. What do you remember from last time? What did we start talking about last time? New topics.
We talked about including multiple predictors in a single model.
Yeah, multiple predictors at the same time. So transitioning from what would be simple regression kinds of ideas to multiple linear regression. Yep. And how does that change the story of how we talk about what the predictors do?
I remember something about using unique now as opposed to not.
Yes. So a slope is a slope, but in terms of how we think about what it represents conceptually, a 1 unit change in x leads to this much change in y as the definition of a slope. It's either bivariate or it's unique. And so up to this point, all of the examples we've seen have been predominantly bivariate, meaning just how does x relate to y, period. And it may take x to have more than one slope to answer that question. So in the last unit, we looked at categorical predictors, for instance, that have more than two categories, take more than one slope. Nonlinear effects of quantitative variables take more than one slope. But those are bivariate relationships. Transitioning into unique relationships is what is the effect of x after controlling for some other covariate? So what does x bring to the table uniquely, so to speak, in predicting an outcome? So that's the big switch in notation and those kinds of ideas. What about effect size? How does the story on effect size change? False alarm, Alex?
I I remember this was around the slide that you started talking about the standardized slope. Is that what it was, or
That's one.
and something with eta squared? But
Yeah.
I don't remember what eta squared was.
Yeah. So up to this point, a standardized slope is the same thing as just a Pearson correlation. Standardized slope is what you would get if you transformed all of the variables in the model to z-scores, where each has a mean of 0 and a standard deviation of 1. Then all of the slopes in the model will be on a scale, a correlation metric of -1 to 1. Now that you have multiple predictors in the same model, the standardized slopes will not be equivalent to the Pearson correlation between those variables. They are going to form something that's more like a semi-partial correlation. So a standardized slope and a semi-partial correlation are very similar. They differ in their denominator, but both of them are a standardized way of expressing what the predictor brings to the model uniquely. And so yeah, eta square then is effect size. So I think that's probably a good place to pick up and talk about those details again. So, and yes, we use this is us as the idea. Let me get a screen share going. The usual pictures here. Come back. There we go. And the slides will help. Yeah, effect sizes. So the idea then, go back to the Ballantine picture, or what I know of as a Venn diagram for a second. So this is slide 10 in lecture 5. So the objective then is to carve up the contributions of the predictor variables in the model into what is unique and what is common. So the good news is that what is common still gets included in the R-square for the model. So the overlap of the predictors does still help in predicting an outcome. The bad news is that none of the predictors uniquely gets credit for it. So it is possible indeed to have a significant model that does not have any significant predictors in it. I know that sounds crazy, but it's possible. If you have a set of predictors that are very highly related to the outcome, but also very highly related to each other, then their contributions may not be significant, when looked at just the unique part, but the common part can still predict the outcome. So yes, it is possible to have a significant model in terms of the variance accounted for by the predictors and yet have none of them be significant individually. So the R-square for the model does include the common parts, but the individual variables do not get credit for it. So that idea here is displayed graphically with this y as being the outcome, has been divided up into 4 parts here, A, C, B, and E. E is what we know of as the model residual. So E here represents the part of y that is unrelated to any of the model predictors. So the unexplained variability in y would be the area E. The area C is what is related to the outcome in terms of both predictors simultaneously. So you can think of that as the covariance between the predictors and the outcome. And then A is what predictor x1 relates to y uniquely, and B describes how x2 relates to y uniquely. So this sort of carving this up into pieces is the object of the game. And it is frequently of interest not just to answer the question, does a predictor relate uniquely yes or no, like significant or not, but to what extent are predictors more related? And so that's where having an effect size is really important, because each of these predictors is still going to have a slope that is unstandardized. It's still in units, dollars, inches, what have you. And so finding a standardized way to express its relationship then allows you to put them against each other and say, well, this predictor has a standardized slope of 0.3, whereas this predictor has a standardized slope of 0.2, therefore the first predictor is more important, so to speak. So effect size is a big deal in answering a lot of questions about the unique contributions of predictors. So then we had lots of formulas. We have, this is the slide that I was thinking of about standardized slopes versus semi-partial correlation. So the semi-partial correlation is the correlation between a predictor and an outcome controlling for the common variance across predictors. It is related to standardized slopes in the following fashion. Both of them have the same numerator. So a standardized slope is the unique covariability between that predictor and the outcome. But the difference is that the standardized slope has a denominator of the unique variance of the predictor, whereas the semi-partial correlation has a denominator of the unique standard deviation. So they're getting at the same idea, just on slightly different scales. In practice, what we end up using is semi-partial correlation as a more general way of assessing effect size. So this is slide 17. So this is known in your output as eta squared. So there's eta squared and there's omega squared. And these correspond to the amount of the R squared that is attributable to that predictor or set of predictors. And omega squared is the same thing except analogous to adjusted R, so corrected for use in smaller samples. So not all software programs give both. I think both SAS and Stata do, although it's much easier to get eta squareds for different combinations from SAS than from Stata. So I'm only going to ask for eta squared type statistics in cases in which both programs will give the answer directly to try and keep it fair. So semi-partial eta square then, in a squared metric, how much of the R square is due to that predictor? So if you just have a predictor that takes one slope to characterize its effect, you can do either of these and it's fine. Where we fall into trouble is when we have slopes that describe the effect of slopes that capture a relationship between a predictor and an outcome where it takes more than one slope to do that. So in that case, we have to lump them back together again to get their joint effect size. So I think that was where we were left off last time. So I think we're starting up about here-ish on slide 18. So any questions before we dive into some new material? No? We're good? Okay. So the idea of lumping together slopes to get a joint test of their significance and to get a joint effect size for them. That's the new thing in this unit. That's it. So it boils down to one new statement in each program that I'm going to show you how to use. So up this point, homework 5 is available. It is a sequential analysis where you add a predictor, then add another predictor, then add another predictor. And so the only new catch is to learn how to test to what extent the predictors that you've added in each step as a set jointly account for significant variance. So that's the new part that we have to talk about today and show you. So for something like these two cases right here, if I had a model that looks like this, I have the first one here, a linear effective age and a quadratic effective age. So we did this in the last unit. This is analogous to the section 2 of the homework you just finished, looking at the linear and quadratic effects of enthusiasm. So in this case, we have to be careful when we think about effect size for beta 1, because beta 1 is conditional. The definition of a linear slope in a model that also has a squared variable for the same, so a model that has a quadratic effect here, the linear slope beta 1 is specific to when the variable is 0. So if you ask for a significance test and an effect size for that, you just have to keep in mind that if you change where the variable is centered, that beta 1 would have a different effect with a different level of significance with a different effect size. So it's conditional. So the best thing to do if you want to convey what is the effect size for how age relates to my outcome would be to lump together beta 1 and beta 2 and ask for a joint estimate of how much of the variance those two slopes working together accounted for. So an eta square for the joint combination is a useful thing. Likewise, down here, same idea, different context. This is a 3-group predictor. So if I have 3 groups, I need 2 slopes. So I have beta 1 and beta 2 working together. If I were to get an effect size for each of them, the sum of those could very well go over what it should actually be for the overall variable, because the contrasts are not orthogonal. They both have a common reference group. So to get a better test, a more accurate test of how group as a concept contributes to the model, it would be good to lump together beta 1 and beta 2 to get a joint test of their significance and their joint eta square for how much of the R square those two slopes working together capture. So those are 2 cases in which we would want to do that type of lumping together to get an effect size. Here's another one. So adding to our box of tools, up to this point, you might call this just either multiple regression or analysis of variance. There's also analysis of covariance. So if I had a model that looks something like this, this is a classic analysis of covariance model because I have a quantitative predictor, we'll call it x1 here, and I have a grouping variable, a categorical predictor. So I have beta 1 as sort of one idea that describes how x1 relates linearly to the outcome, and I have beta 2 and 3 in this case, which describe differences between these 3 groups and how they relate to y. So if I were to put this model into SAS or Stata, I would get a model f-test, right? Like that's the first box that shows up on your output, the f-test for the model. And it would tell me as a set how well beta 1, beta 2, and beta 3 work together to create a significantly related predicted outcome with respect to the row 1. So the joint test of all 3 of those slopes will be provided by default. But in order to answer the question, okay, what's the unique effect of group after controlling for x1, I would have to ask for a second f-test that only lumps together beta 2 and beta 3. So that's what I want to teach you how to do that. So how do we do that? It is a new statement in SAS called contrast. In Stata, the same thing is available via test within the regress command. So these are general strategies to lump together multiple slopes to get a joint test of their significance and a joint effect size. SAS gives you both within this contrast. Stata does not provide effect sizes directly. It does give an F-test with a significance value associated with it, but it doesn't give you the effect size. But we can do so by estimating separate models with and without the terms to get the unique sums of squares associated with those terms. And so I can show you how to do that in our example. Let's see, several of you have had regression type coursework. Did you do like hierarchical regression or stepwise regression in those? Does that sound familiar? Doesn't sound familiar? Okay, well, good news is that this is a special case of that too. And so homework 5 is structured in a hierarchical way because that's a common thing that people do. The first layer, so to speak, in building a model would be variables that you expect to be related to the outcome that nobody really cares about. People call those controls, or they call them covariates sometimes. The second layer would be things you actually do care about, and then you would want to know to what extent does the set of new things significantly increase the R-square. Well, it turns out the tests that hierarchical regression programs provide are the same thing as what I'm talking about. A joint F-test for those new terms tells you directly whether the change in R-square is significant. So that's the way that your homework is structured. That way, both programs will provide those significance tests, and you can work between the models to get the R-square. So in Stata, here's how the workaround would be used to get an effect size for a joint combination. So first step is to get the full model that has all of the predictors of interest, and then you would also get the total sums of squares from that model as well. So for instance, if I have this model right here, and what I want is to get a joint effect size for beta 2 and beta 3 together, here's what I have to do. I estimate the full model that has all three slopes. I then estimate a reduced model that has the slopes removed that I want the effect size for. So I see what the sums of squares would be without them. Then I compute the difference. So that tells me indirectly how much of the captured information is related to the two slopes that I'm testing. And then I can compute my semi-partial eta square, which is the difference in those sums of squares over the total. And so I have an example of how to do that in Stata so that you can calculate the same semi-partial R-squares that are given automatically in SAS. There is another command in Stata that gives sums of squares, but it's related to partial and not semi-partial, which is not the same thing. So unfortunately, I have not found a way to do this that doesn't involve multiple steps in Stata. All right, so do you want to see how this works? Why not, right? So let me go out of this and open up, this is example 5a. The good news is that this is the last example using the same data set that we've been playing with all semester. The next one and the next ones I have new data for you in case you're getting sick of the general social survey. But it's helpful sometimes for continuity to layer these things in, so I've made a choice to use the same data. But this is the last time you'll get to see it. So what we are doing is taking the three separate models that I fit in example 4 and fitting them simultaneously. So in example 4, we had income as the dependent variable, the outcome to be predicted, and we first predicted it with a 3-category version of working class, low, middle, and upper. We then predicted it with a quadratic effective age, so linear and quadratic terms for age. And then in the last set, we predicted it with a piecewise slopes version of education, where we had the effective education from 2 to 11 years, 11 to 12 years, and then after 12 years. So I'm going to put all of them together at once. So one big model is the objective here. So the import steps in this are the same as usual. Tell it where your stuff is. Import this as an Excel file. And then we got to make all the new predictors. So up to this point, I have compartmentalized the example so that I have a data step that makes the new predictors, and then I use them immediately in the model. And then I have another data step that makes new predictors, and then I use them immediately in the model. And I had done that based on feedback from previous classes that they didn't know where to look for examples on how to make the variables. But the way that I do it in practice is much more like what I have in this handout. Generally speaking, I organize my code to do all of the data manipulation steps that I'm going to need in one step. So I make all of the centered predictor variables, I do all of the recoding, I do all of the selection, I do all of that, and then I do the models. That way, if I open up the file again, I don't have to run little chunks of code throughout the program. I just have to run the one step at the beginning that gets me back to where I was with respect to the data. So this then, that whole chunk of code right here in SAS does everything in one step that I'm going to need to build this model. So a reminder that you have to have code to create new variables inside a data set combination. So you have to tell it which data set you want to do stuff to. I'm first making 2 new blank variables that I'm going to fill in with my dummy codes for low versus middle and low versus upper. So this is the same thing that we had an example for. I am then centering age at 18. So that's going to be my linear and quadratic effects of age that go into the model. And then the piecewise model, first generating 3 new blank variables and then filling them in with the values needed to create the coding scheme that we had before, where if education is less than 12, then this variable is going to be active. If education is greater than or equal to 12, then these variables are active instead. And then last but not least, selecting cases that are complete so that everybody who has all of the information that we need will be included in the analysis and no one else. Stata code then looks very similar. Step 1, tell it where your stuff is. Import the file from Excel. And then the same data generation steps as to creating these 2 new blank variables, filling them in with zeros and ones, creating my age variable that's centered at 18, and then creating my piecewise slopes variables based on less than or equal to 12, and then labels. Okay, so any questions on the setup or the code? So you've seen all of this before. I'm just doing it all in one step at this point. No? Good? Okay. So then here's my model. What do you think of that? Now just think, if I hadn't showed you this on the first day of class and said, this is where we're headed, exactly. This may have been panic-inducing, but you look at this now, right? And it's not panic-inducing. It's like, oh, well, that's my intercept. I know what that means. The intercept is what? Let's do a little review. What's my intercept? In general, and then in the specifics here. In general, what's an intercept? You are here. Yes. Mathematical definition.
Where X is 0 and Y is not.
Right ideas, not quite the right ordering, I think.
Or Y is 0, X is, well, where pass.
We're pass. Okay, Jerome is throwing the ball to someone else who wants to catch it and help him out. He slept for 2 hours last night. We got to cut him some slack.
Is it the value of the outcome variable when the predictor variables are 0?
There you go. Yeah, when X is 0, it's what Y is. So when X is 0, at this point is all this stuff. So the intercept, beta 0, is going to provide the expected income for somebody who is, and this is where we have to know how we've defined 0, in the low group. They rated themselves as being part of the lower class. And age 18, and the reference point for the education variable was grade 11. So somebody who is 18 made it to the 11th grade and rated themselves as lower class. That's who the intercept is for. So then conceptually, how many slopes do I have in this model here? How many distinct slopes am I asking it to estimate? Seven. You know an easy way to know? Look at the highest number for the beta. It goes up to 7. Because beta 0 is the intercept, doesn't count. So I've got 7 slopes. But how many different variables are those 7 slopes representing? Like as a construct, how many separate predictive constructs? Yeah, just 3. Because it takes 2 slopes to talk about the effect of 3 category working class. It takes 2 slopes to talk about the effect of age because it's linear and quadratic. And it takes 3 slopes to talk about the distinct effect of education within the separate regions as I've defined them. So I know based on that I'm going to want to ask for additional information that lumps those slopes back together that refer to the same idea. So here's what I have then in terms of code. First, the familiar part. There's my model line. So nothing different than what you're used to. The variables that go on your model line, first is the outcome, equals, and then the predictor variables as you've created them. So the centered or recoded versions of the predictors in which you've redefined what 0 means. That's what goes on this line. There's also one more thing that I'm asking for with an estimate statement here. And because the model gives me low versus middle for my grouping predictor and low versus upper, it's not going to directly give me middle versus upper, and so I'm going to ask for it here. So the difference of the slope for low versus middle and low versus upper, that difference in slopes gives me middle versus upper. So it's the same idea as what you just did in the golf assignment, getting the differences in outcomes between the non-reference groups. So this is not new. This is not new, it just has more stuff on it than before. Okay, with me so far? Yes. Okay, let me go down to the state of code. We're skipping a bunch of output for a moment to show you that that much isn't new either. So this is on page 4. Here's the corresponding state of code for the model equation. Income is the outcome variable, that comes first. Then we have all of the predictors put together. The hashtag is used to define an interaction term, which is the interaction of the age by itself, which makes the quadratic term. And then the comma denotes the level here. And then I have a lincom statement that gives me the model implied difference of middle and upper, the same as before. Okay. Let's stick here with stata for right now since we're already here. The new parts. This is the new part. This is the new code for this example that you need to finish homework 5, which is due in 2 weeks, so you got plenty of time. So why do I need to write this? Let's look at what happens by default. So I've got both SAS output and stata output in this handout. Let's do stata first because it has less output to consider. So the first set of boxes here you are used to. So I have bolded the ones that we want to pay attention to. What's this thing right here? 136 tells me what?
Residual.
Residual.
Or E sub I.
One more word after it.
Variance. Alex.
Variance.
Yeah. It's a team effort. I like this. Yes, the variance of the E sub I residuals. Yep. So the collection of them across people, how much they vary. Conceptually, 136 residual variance, it is how much unexplained variation there is in this outcome. So all the reasons that some people make more money than others that have nothing to do with their age, their self-reported working class, and their education level. So is that a lot? Is 136 good? The correct answer is, I don't know. All I know is that this is relative to how much variance there was in income in the first place, right? Because this is left over. So I need to know how much variance there was in income in the first place. I could get that from the empty model, or I could look over here at my friend R squared. So 0.29-ish, what is that telling me?
Portion of variance accounted for by the model.
Yeah, 29% of the variance in income is accounted for by the model. 136 is the amount that is left. So these are in different scales. R square goes from 0 to 1, where 1 means 100% accounted for. So it's a proportion. Whereas 136 is an amount that depends on the units. So is 29% significant? What do you think? Yeah, we got an emphatic yes. Correct. How do I know that? What do I look at?
The F and the P.
Yep. Here, there's my significance test. So F, 7, 726, those are my degrees of freedom. It's 7 because this F test is lumping together all 7 slopes that are in my model. There are 726 more slopes I could have put in, but I didn't. And 42 is the contribution per slope. So F is scaled in a per slope metric where 1 is like the worst you could do, meaning that your slope didn't do any better than just a random variable. So the p-value that goes with it is 0 to 4 decimal places, meaning that we would see a joint contribution of these 7 slopes this large or larger, less than 0.001% of the time. And if I wanted to worry about the effect of sample size, there's an adjusted R-square that adds a correction for n to the formula, so it's 28% instead of 29%. But either way, it still looks pretty good. So this tells me on the whole how working class, age, and education work together. But I may also have hypotheses about each aspect. So we can go through the solution. So I would call this the solution for the fixed effects because these are the betas that the model estimated for me. So in Stata, much to my dismay, the constant is at the bottom. That's my fixed intercept. It's negative 3.7. Does that strike you as odd? That you can make negative $3,700? Yeah, that can happen. So remind yourself the intercept is conditional on predictors being 0. It is an 18-year-old with an 11th grade education who put themselves in the lower class. That type of person may not exist in the data in that combination. So even though we've done our best to make the predictors interpretable, in combination you may not see all of those align. But that is what the model says as our "you are here" sign. Then if we go through the coefficients, those two, 6 and 7, those tell me how each of the alternative groups differs from the low group. So this is our working class categorical predictor. So the middle group makes $6,000 more than the low group, and the upper group makes $7,200 more than the low group. And those are both significant according to my p-value. So is that the end of my sentence, what I just said? Is that enough, or do I need to add another caveat? The middle group makes $6,000 more than the low group. The upper group makes $7,200 more than the low group. Both of those are significantly positive. The end. good enough, or is there another caveat needed?
I'm assuming that there's another one needed.
Yeah.
So we have the lower versus the mid and the lower versus the upper, but we don't have the mid versus the upper. Is that the one that we're going to look for?
That is right down here. So the Lincom statement that I asked does give me that. So the difference of the 6 versus the 7.2, that's the coefficient right here. So that does give me the remaining piece of that puzzle with respect to how middle and upper differ from each other. They don't differ significantly, but that is not yet the caveat I'm going for.
Do you have to compare the slopes to each other to make sure they are different from each other?
Well, that's what this Lincom statement actually did. It directly contrasted the difference of the slopes. 7.2 minus 6 is a difference of 1.1. So that answer simultaneously tells you if the difference between medium and low and the difference between upper and low are the same. It's easier to think about that as just it's giving you the difference of middle versus upper directly, but that's not it yet.
Are we looking for the unique part of
There
it?
it is. Yeah.
All right.
So how do I add that to the sentences?
No clue.
So I would add in something like, after controlling for age and education level, these are the differences between my three groups. Something like that. After controlling for the other things, these are the unique differences, because these are smaller than what we saw in example 4. I have a table actually that compares these, I think, at the end of this, but they are smaller differences than what we saw before. Because do you think that the self-reported group, whether you refer to yourself as lower class, middle class, or upper class, has something to do with your education level? Probably. It may have something to do with your age. So to the extent that education, age, and class membership are correlated, each of these effects is going to be different when they're pooled together in the same model in which they become unique than when they're in separate models in which they're just bivariate. Cough, cough, quiz question. The only time in which you would expect the predictors to have the exact same effects when they're by themselves versus in combination of others is if the predictors are uncorrelated. That's the only time that would happen, and that's pretty rare outside of experimental designs in which you set it up that way on purpose. Okay so far? So then we have the coefficients for age. So at age 18 is what that slope refers to. So 1.06 is the change in income per year of age at 18. That positive linear slope for age becomes what as age increases? There's 4 choices here. Make this a multiple choice question. The quadratic slope can take this linear slope and make it more positive, more negative, or less negative. Which one is this?
More negative?
This one is a positive number.
More positive.
This one is a negative number.
Less positive.
Less positive. Yeah. So it's like approaching the top of the mountain. Like the slope is positive at 18, but it's slowing down. And eventually it's going to tip over and become a negative slope. So as it's centered over here, I would say it's a positive slope being made less positive. If we had centered age at the middle, then it could be a 0 slope that is more positive as you go this way or less positive as you go the other way. And it's less positive by twice the quadratic coefficient. That's the key to remembering this one. And then last but not least, and that is after controlling for the other predictors as well, the unique component. And then each of these 3 slopes here describe the effect of one more year of education within its separate segment. So less than high school describes the effect of one more year amongst people between 2 and 11 years. So in those people, more doesn't help. The grad high school describes the effect of going from 11th to 12th grade education, and that was significant before, it's not significant now. So after controlling for age and working class, there is no longer a significant benefit to graduating high school. Fortunately for all of us, though, the third slope, talking about the effect of one more year of education past grade 12, remains significantly positive. So we can look at, so far, the overall test of all 7 slopes put together, and we can look at each individual slope. The last thing I want to show you is kind of like the middle ground of the two, because the model as a whole doesn't answer the question of how does age relate to income? How does education relate to income? So that's where we have our new friends, the test statements. So this is the new part here. The first test statement I have included for pedagogical purposes only. It is to show you what it would look like to ask for this set of results that are already given to you by default. So the structure of these test statements is that you list in separate sets of parentheses each slope that you want to be tested against 0. You can test it against other numbers too, actually, but the zeros are in here to make that explicit. So I am listing all 7 slopes simultaneously. In Stata, by the way, if you exceed, if you make a line that's one command span multiple physical lines of code, you have to put these 3 slashes in here. It's what's known as a line continuer. So otherwise it doesn't understand that this is all supposed to be one statement, because it only reads to the end of the line. So this test statement gives you the exact same thing as the f-test for the model here. There are certain types of models in which it's not provided by default. So knowing how to ask for it is a useful thing, but it's mainly for pedagogy here. The other 3 are not provided by default and are customized for this example to answer very specific questions about how the predictors relate to each other. Question, renaming all variables to be one letter to make it all fit. That is another strategy. Or you could just type out 200 characters on the same line and then, drag your slider bar over. That's also an option. But yeah, if you want to make it the line continuer. I am told, by the way, that in later versions of Stata that this is either discontinued or not necessary in certain cases, but if you want your code to be backwards compatible, I would include it. So the line continuer is your new friend to keeping your code onto the same screen. But these test statements, so these are examples of how you would lump slopes together to answer specific questions. So the first test statement right here lumps together the 2 slopes that relate to working class. And so that gives me a joint test of whether there are any differences across the 3 groups, because it takes 2 slopes to recreate all 3 means after we factor in the intercept. The second test statement here lumps together the 2 slopes related to age to get their joint combination that describes whether age significantly predicts income. And then the last one lumps together the 3 slopes related to education. So you can lump together whatever you want. This is a general procedure that you would put together whatever combinations make sense based on the context of what you're doing. In this context, it's a way to get multiple fixed effects related to the same conceptual predictor to be lumped together to get a significance test of those. But there are other instances in which you might want to do this as well. So we'll see several examples of this.
For those 3, the intercept, is that only the intercept for the 0 of that group, or is it the intercept for all of the predictors combined?
It's one intercept for all predictors combined.
Okay.
And
So the intercept for each of these three is still the 18-year-old lower class 11th grader. Okay.
yeah, 11th grade education. And so because I have an intercept for the low group, then I only need 2 slopes to get me to each of the other groups, and then the third difference is a linear combination. So the 2 slopes combined with an intercept for one of the groups gets me all 3 means. And if I had 4 groups, how many slopes would I need? If I had 4 groups, how many slopes do I need to differentiate my 4 groups? Yeah, 3. It's always C minus 1 for the number of categories. So then the F tests that I've requested show up down here. So the first one, the one that I did for pedagogical purposes, lumping together all 7 slopes, the F for that is 42.09, which is not at all coincidentally the same 42.09 that's up here, because that's what it's doing. The other ones are the new ones. The idea of lumping together the 2 effects of education. That gives me an F of 21.82, which is significant. Lumping together the 2 slopes related to age gives me an F of 41, so that's significant. And then lumping together the 3 slopes for piecewise education, which is also significant. So in the write-up that goes with this example, then I would report these Fs in addition to the one for the model, because they answer a more specific question about the unique effect of each combination of slopes that it takes to represent a predictor's relationship with the outcome. Okay, how are we doing? Is that waving or question?
Oh, that was a question.
Okay, hit me.
So like in our next homework, are we going to answer something like that within our drop down or multiple choice, where we're going through the multiple Fs and I guess saying if they're significant or not?
You'll have to decide if they're significant or not, and I think you have to decide on the degrees of freedom.
Oh, okay.
But you will have already generated the Fs for the green box questions.
Got it. Cool.
And if you generated the right F, then you should have the right degrees of freedom for it. Because each of these, the numerator degrees of freedom is the number of slopes you've lumped together. And the denominator degrees of freedom is the same in all of them, because they're all based from the same model that has 722 slopes you could have added. So what you're going to be doing, then I actually have a little spreadsheet that I pulled up that I made from last year, is something that looks more like this. So I will post this for you after class, but this is designed to reinforce the idea of what is old and what is new. So if I start, say, with an empty model, and I have only a fixed intercept in the model, then the mean square error for the residual variance, let's say it's 200. If I have no predictors in my model, then what I'm calling, stop it, residual variance is actually all the variance that there is to be had, right? Remember that from before? Empty model has no predictors, then the residual variance is just each outcome deviated from the mean, which is just all variance. So then the model R square for that would be 0. That's my baseline, haven't explained anything. That tells me how much variance is up for grabs. So then I think your first model, I ask you to add 1 predictor. Let's say then that after adding that 1 predictor, which we'll just say predictor A, the residual variance goes down to 180. Well, relative to the 200 that we started with, that's a 10% reduction. So how do I know if that 10% reduction from adding predictor A is significant? Where do I look, or what do I have to ask for?
We have to look at our F tests.
That's one place I could look. So the F test for the model tells me whether the model generated a significant R-square, and if the model has only one predictor in it, where else could I look to get the same information?
Our t-test, or which, yeah.
The t-test for what?
I was gonna say the t-square would be the f, but
No. That's true. The t for the slope. So if
Got
you
it.
look at the test for a specifically, the a slope estimate divided by its standard error is a t. The p-value that goes with that t is the same p-value that goes with the f that you would get for the model, because t squared is f in that case. So either way you look at it, the output is directly going to tell you whether that 10% variance accounted for by predictor A is significant. And if we talk about change in R-square relative to the previous model, I had nothing in terms of prediction. Now I've got 10%, so that's a change. So those two are telling me the same thing. Relative to an empty model with no predictors, if I add one predictor, the R-square is its change from 0. I have a significance test directly for that via the t for the slope or the f for the model. 6 of one, half dozen of the other. Okay, with me so far? Now, next step, I say leave in predictor A, add in predictors B and C. Okay, I can do that. So let's say that you do that. The residual variance goes down to 140, which relative to the 200 that you started with brings you up to an R-square of 0.3. How do I know if that R-square is significant? So the overall model accounts for 30% of the variance in my example. How do I know if that's significant?
Wouldn't we do the f test again?
Yeah, the
Or-
model F, the
Yeah.
one that's provided for you, directly tests that. So F is a per slope statistic. So it's variance, or let me put it this way. Information captured per slope is the numerator of F, divided by information left over per slope left over is the denominator. So F tells you on a per slope average how well the model did. So we don't have to do anything special to get the F that tests my R-square. Now, however, relative to the previous model, the change in R-square that resulted from adding in B and C is a change of 20%. How do I know if that change in R-square from adding in B and C is significant? This is the new thing we're talking about today. I need to ask. Because the overall model F that tells me about R-square is not the same thing as testing whether the difference in R-square relative to the previous model is significant. So conceptually, what I need to do is isolate the two new predictors whose slopes are responsible for the change in R-square of 20% relative to the previous model. So that's where we would do something like this. So this is what it looks like in SAS that we haven't gotten to yet. This is what it looks like in Stata. So I lump together the slope for B with the slope for C, and if that F test is significant, that tells me whether adding B and C significantly increased the R-square. So what happens as we talk about variances versus R-squares is in opposition of each other. Cough, cough, homework question. As we add predictors, what should happen to my residual variance if the predictors are any good? Does it go up or does it go down? Down. Residual variance is unexplained information. As we add predictors to the model, the amount of unexplained information, residual variance should go down. At the same time, then, what should happen to R square as we add predictors? Goes up. Because R square is proportion of variance accounted for. So these are opposite ideas in terms of what they represent. R square is how good the model did. Residual variance is how much is still missing. So then likewise, if I have my model with predictors A, B, and C, and I do another model where I add in 2 new predictors D and E, then let's say that brings my residual variance down to 80. That's a total R square relative to the 200 that we started with of 60%. The F-test for the model is going to lump together all 5 slopes and tell me whether or not that model R square of 0.6 is significant. But to answer the question as to whether my new predictors D and E helped, what do I need to do?
Like we did below where you're doing it. I know the C dot for theta. Yeah.
Mm-hmm. I need one of these, but with D and E in it instead. So this is the one new concept for this unit. And when you add in predictors in this kind of stepwise fashion, you can watch the R squared change between steps. And so I have questions on homework 5 as to what is the difference in variance accounted for. This is the one instance in which you're going to get a calculator out. Because it's easier, it isn't worth the amount of effort it would take to program it. So you get an R square for each of your models. I want you to use simple subtraction just to find the difference between the R squares. The significance test for that R square then is provided by these test and contrast statements. But if you didn't want to do it in a sequential fashion, then I want to teach you how to take one model and answer all of these questions. Because you don't actually have to add them in step by step to get the contribution of each. You can ask it to provide the contribution of each from one model. So that can save you time and is especially useful in situations in which there's not a clearly undebatable ordering to how the predictor should go in. Okay. Questions or comments? How we doing? Okay-ish? All right, then let me back up and show you how to do the same ideas looking at the joint contribution of a set of predictors in SAS. Rather than test, it's contrast. So the syntax looks a little bit different, but it's the exact same concept. So the first contrast that I have here is for pedagogical purposes. It lumps together all 7 slopes to recreate what the model F-test would have been, so what it's doing under the hood for you. And the way that we do this is by listing each predictor whose slope we want lumped together, followed by a 1. It's not always looking like this, but when your predictors are each being treated as quantitative, this is what it looks like, which is every example I've done for you so far has had that same structure. And then the commas are used to separate them. So it's not asking for the one number of the slopes being added together. It's asking for a joint test of separate slopes. So the commas are very important to separate out each of the components that you want lumped together. So by listing all 7 slopes, each with the 1 after it separated by commas, I get the F-test for the model. And then the 3 specific instances that we saw in Stata. The first one tests the 3 category grouping variable, the 2 slopes for that. The second one tests the 2 slopes related to the effective age. And the third one tests the 3 slopes related to the effective education. And these purple words here, it insists that you provide a label, but you get to write whatever you want here. So this is your trail of breadcrumbs in looking at a whole list of F statistics to make sure you provide a decent label so that you know what you're looking at later on. Stata does not require that, but I always do the same thing by using a comment. And then this part is not strictly necessary, but I use it so that I can do math on the slopes to generate effect sizes for each specific one later on. So any questions on the contrast statement as it is demonstrated here? Joint f-tests for combinations of slopes. That's the goal. So let me show you what happens then. Here is the model test for all 7 put together again that we went over and the Stata output for. So there's my f for all 7 slopes for the model lumped together. There's my r-square of 29%. Here's my residual variance, the amount of variance left over. And then here's a box that I normally don't bother to show. Each separate effect in the model has a sums of squares associated with it. So then it's just a question of asking SAS to lump together the ones that I want so that I can get custom hypothesis tests for sets of slopes together. So SAS gives me semi-partial eta square, so the labels here, semi-partial omega square, and confidence intervals for that, for each of the parameters. But in each of these cases, the semi-partial eta square that's given for each of these is going to be less useful than the one that I get out of my contrast statement, because I want to lump them together to talk about their contribution to the r-square. So here are the 4 f-tests that I requested via the contrast statements. The first one with the f of 42 is the same thing as the model test of the r-square, and the other 3 are the test of the increment to the r-square that arises from the 2 slopes for work class, the 2 slopes for age, or the 3 slopes for education. So you don't have to enter your predictors in sets and look at change in r-square. You can have one joint model and look at the change in r-square that is attributable to each set of slopes in one fell swoop. Unfortunately, Stata does not give you the sums of squares or the effect sizes directly. They only give you the f's, which is why I had you do it in a hierarchical way in homework 5 to get around that problem. So then here's the effect size that goes with the overall model and with each chunk. So semi-partial eta square is the amount of the variance that's explained due to that particular variable. So the first f-test that has all 7 slopes gives me the overall model r-square. The others then tell me that the 2 slopes for working class are responsible for 4% of my 29%. So the 0.29, 0.04 of it is because of working class, 0.08 of it is because of age, and 0.08 of it is because of education. So these are effect sizes that tell you the relative importance of each predictor variable after factoring in however many slopes are necessary to describe it. Now, I'm no mathematician, but I'm pretty sure that 0.08 plus 0.08 plus 0.04 is roughly 0.20, right? Give or take? But my overall model r-square is 0.29. Where'd the rest go? I'm missing like 9%. Where'd it go? Yeah, I can't decipher the gestures, sorry.
Well, I was gonna say, is that what's in omega? When I was looking at the table.
Omega is the same thing but corrected for sample size.
Oh,
in the
got
same
it.
way that you have an r-square and then an adjusted r-square. It's the same idea. But no, I said the model counts for 29% of the variance, but the 3 pieces that I've requested here only add up to 0.2, 20 of it. Where's the other 9%?
Would it come from when you combine those 3 separate predictors together?
Yeah, the other 9% We go back to my picture here. It's the area C, the part that they have in common. So none of the individual predictors or sets of predictors gets credit for it, but it's there. So the overall R-square will be higher than the semi-partial R-squares to the extent that the predictors are related to each other. Yes, indeedy. Okay, how are we doing? Okay, feel like you could do this? We'll find
So
out,
in a sense, that C is the Kevin from the This Is Us example, where didn't really clean the room, or we could have done without his cleaning because everything else was there.
Yep, the C are the rooms that multiple people claim to have cleaned, and we don't know who cleaned them, and so we can't give anybody a Nintendo game.
Got it.
And yes, it would be Kevin that's slacking off of all of them. Odds are good. He's used to relying on his good looks and charm to get his way through the world. Yeah, you're Mandy Moore, Alex is my Kevin. So we'll just leave it at that. There's a simpatico there. But anywho. So last but not least here, I demonstrated how to take each of the unstandardized slopes and also convert them into Cohen's d and r effect sizes using their t-test statistics. That's not something that I'm going to ask you to do, but I think it's something that's useful to know how to do. So I did that by saving the slope data set in SAS and then doing this math on it. And I think that's about it for this handout. I have, the state of people. That's right. So the last but not least then, Stata gives you these F-tests for the joint contributions, but it doesn't give you the eta squares for them. So here's how you would go about doing it. So I had to do it in pieces. I first estimated a reduced model that did not have working class in it, so missing the slopes for beta 1 and beta 2 on purpose, because then I'm going to get the sums of squares that are attributable to the others and use that number to find the difference. So that gives me the eta square for age that I had gotten directly in SAS. So the idea is you have your full model that tells you what the full sums of squares that's accounted for is, and you have the total that includes the residual variance. You estimate reduced models omitting the thing you're trying to get the effect size for, so that you can see how much of the sums of squares would be reduced because you omitted it. And so then that's your sums of squares that forms your eta square. So then full model minus reduced model without the terms I care about divided by the total gives me my semi-partial eta squared. So that's the 8% that goes with working class. I did it again, putting working class in, but then taking out education level. And that gave me the 8% for education. And I had done it, I think, one more time for age, possibly. Yeah. And so then here is a table that shows the difference in what we found for each of these predictors by itself in a bivariate relationship versus what this example shows them when they're all put together again. So in separate models, each of the effects accounted for more sums of squares and a higher R square than what it is when they're jointly together. So, and then here's the difference in the coefficients from separate models versus the combined model. Just making the point that the difference between bivariate and unique is greater to the extent that your predictors are more related. So that was the point of that story. And I think I have words. Yeah, and that's it. So point of the story, you can put together any sets of predictors into the same model that you want. You get a direct test of each predictor's slope's unique contribution via the T for it, but you can also ask for joint tests that lump predictors together in meaningful ways to get at more general hypotheses about the effect of a predictor when it takes more than one slope to characterize it. And that's it. questions? So let me ask you this. In terms of the schedule, I only have a few more PowerPoint slides to do, and then the rest of this lecture is done. And I have videos from last time going over example 5B, which is really just more of a review. Would it be a good use of our time to go over 5B together, or would you rather watch the videos that are outside of class and then maybe have a smaller class session next time? What do you think?
I could do either, so I'm fine with whatever.
Same for me.
We're flexible.
My question would be, in going over 5B, do you find students generally ask the same questions semester to semester in that, in watching the video and not doing it live, we're not going to miss out on much, or?
I just invented it last semester. So last semester was the first version that I did a 5A and a 5B to make separate concepts. But I'm sensitive to the idea that I think folks benefit from different amounts from review than others. And so I want to be efficient yet thorough, if that makes sense. Otherwise, we could, yeah, we're way ahead. This is great. How about this? How about we make, I'll make a plan for next time to do just the beginning part with the stuff we haven't talked about in the PowerPoint, and then people who want to stick around for example 5B can. Would that work? Okay, and if you want to take a shorter class, then that's fine too. Does that work? Okay, let's do that then. All right, so shorter class next time for those of you who feel like you don't need the review or you just really need a break from Zoom. One of the two. All right, then that's it for today. Let me know if you need anything. I will see you on Thursday.